How's it? So today we're going to be looking at some more Euclidean geometry. In this diagram, PQRS is a cyclic quadrilateral, which I've highlighted in blue. RQ is equal to RS, that is shown with these little lines, and ST is a tangent, which is shown in green. And they've given us R2 to be 68 degrees, and with that we need to determine the size of reasons, the angle P. So the angle P is here, and it's inside our blue cyclic quad. So we're going to be using a cyclic quad theorem. That says the exterior angle of a cyclic quad is equal to the opposite interior angle. So applied in this question over here, the 68 degrees is an exterior angle of the cyclic quad. And then I follow that exterior angle down to the opposite interior angle, and it tells me they are equal. So P is 68 degrees, and we simply write that up like this. We firstly have to state which angles we recognize were equal with that theorem. So we recognize that R2 was equal to P, and they both have a size of 68, and our reason was exterior angle of cyclic quad. And we're going to get 1 mark a pop for our statement and for our reason. Next up, we need to get the size of Q1. Now I'm noticing Q1 is inside of a triangle, and it's quite a special triangle. 2 sides of the triangle are equal, which makes it an isosceles triangle. And we have a couple of theorems with isosceles triangles. If I know that these 2 sides are equal, then I know that the base angles are equal. Utilizing the theorem angles op equal sides. If I have equal sides on either side of the triangle, I go to the opposite angles and those guys will be equal. So from that we can conclude that Q1 is the same size as S2 for this reason. And also with this orange triangle, we have the exterior angle of the orange triangle. It's 68 degrees. So if I say Q1 plus S2, they're both going to equal 68 degrees when I add them together because of this theorem. Exterior angles of triangle. So I add together the opposite interior angles and they give me this exterior angle over here. So apply to our scenario, if I say S2 plus Q1, it's going to equal 68 for this reason. And then after I've written that up, we know that S2 is the same size as Q1. So I'm going to change this S2 to a Q1. And Q1 plus Q1, it's like X plus X. So it's going to be 2Q1. And then I'm going to divide both sides by 2 to get Q1 on its own. And now we officially have the size of Q1 to be 34 degrees, which I have marked off on my sketch. 34 plus 34 will definitely give me 68. And let's have a look where the 2 marks come from. We're going to get 1 mark for our statement over here, and 1 mark for this big statement of how we got Q1. And lastly in this question, we need the size of S1. Now, angle S1 is sitting in between a tangent and a chord. So we're going to utilize the tan chord theorem. Tan is short for tangent, which states the angle between the tangent and the chord is equal to the angle that this chord subtends. So we've got to find out the angle that is being subtended by the chord. So we go to either end of the chord and follow it down. And if I follow those ends down, it takes me to Q1, 34. So S1 will be equal to Q1, 34 degrees for this reason, tan chord theorem. And we simply just write it up like this. S1 is the same size as Q1, which are both 34 degrees for the tan chord theorem. And let's have a look where the 2 marks come from. We clap 1 mark for the statements and we clap 1 mark for the reason, and then we've officially waxed this question, my bro. Coming in hot with question 9. Okay, we need to determine with reasons any 3 other angles equal to D1. D1 is 37 degrees and it's sitting over here, and I can see D1 is nested inside a bow tie, my friend. And the theorem that is known for the bow tie is angles in the same segment. So we've discovered our first other angle equal to D1. It's A2. A2 will also be 37 for this reason, angles in the same seg. And we simply just write that up like this. We show the two angles we recognize are equal due to angles in the same segment, and then we state their size. Okay, on to the next one. Okay, now this is where this piece of information becomes very important. The line BA is going to cut angle CAD perfectly in half. So it's a very snooty way of telling you that angle A1 and A2 are equal. It's saying this orange angle is going to be cut perfectly in half by this green line, and you're going to get 37 for A1 and 37 for A2 over there. Can we write that up just like this? A1 is the same size as A2, which are both 37 degrees, and we knew that because BA bisects the angle CAD. And now I smell some sneaky weasels. There are some radii in the mix. They're a bit hard to see. So I see 4 radii actually. So let's start off with these two radii, FA and FC. So if they're equal in length, it means that the base angles must be equal. So C2 will also be 37. And we simply just show the relationship between the two. A2 equals C2 equals 37. And our reason is angles op equal sides. That's a property of an isosceles triangle. And lastly, I'm going to do you one better. I'm going to get you a fourth angle equal to D1. So I see another isosceles triangle over here. So AF is a radii, FD is a radii, which makes this orange triangle an isosceles triangle. So D3 will also be 37 degrees for the same exact reason, angles op equal sides. And quickly having a look where our 4 marks come from. First mark comes from the statement over here, and the reason for angles in the same seg gets you your second mark. And then you get 2 marks for any of these 2 statements. I went a bit above and beyond getting 4, but I like to go a bit above and beyond with Euclidean. It always helps. Next up, we need to show that DG equals GC. Now I'm noticing that DC is a chord. So if I prove that this line from the center is perpendicular to the chord, it'll prove what they're asking me to do. So I want to get G1. G1 should be 90. So to get G1, I'm going to target this triangle, because I already have one angle inside of that triangle. So all that's left is I need to get D2. And that's where this piece of information becomes important. AB is a diameter. So if I follow my diameter down from either end on the circumference, it's going to take me to a 90-degree angle because of angles in a semicircle. So if I know that the whole of D is 90, I can quite easily calculate D2 because I've got D1 and D3. So let's go ahead and jump into that statement and reason. So I'm going to state that D2 equals 90 minus 37 minus another 37, because all 3 of these add up to 90. So it stands to reason if I take the 37s away from 90, it's just going to leave me with the size of D2. And don't take chances, straight in the calculator. So we slap that in there, clap it equals, and we get 16 degrees for D2. And now we're going to come back to this orange triangle to get the size of G1, simply using interior angles of a triangle. All of them need to add up to 180, so it stands to reason that G1 will be 90 minus this big angle minus this 37. Okay, and I know exactly what this is going to give me. It should give me 90 degrees, but double check just for comfort's sake. And you see that it claps me the 90, boys. And now that we have G1 to be 90 degrees, we can actually leap to our conclusion that DG is the same size for GC for the following theorem. Line from center perpendicular to chord. If I have a line running from the center, that is perpendicular to my chord, then the chord is bisected. It's cut in 2 equal parts. So DG equals GC for this reason. Line from center perpendicular to chord. And I simply just write up my conclusion like this. DG equals GC. Line from center perpendicular to chord. And then quickly having a look where your 4 marks come from. Reason over here, the statement for D2, the statement for G1, as well as the reason for your conclusion. And the last question here gives us the radius to be 20 units, and with that we need to calculate the length of BG. And how we're going to do that is with our 90-degree triangles. We're going to use SOHCAHTOA. So if the radius is 20, then the length of DF is 20. And then what I'm going to do is use SOHCAHTOA to work out this side, FG. So we're going to be working in this triangle, DGF. And in that triangle, I have the hypotenuse. You see how the 90 degrees points to it? So I need something with hypotenuse, so I'm going to be using sine or cos. And now I'm going to analyze what I want. I want the side FG, which is opposite to the angle. So I want opposite in the mix, so we're going to be using sine. So we're going to start this process off by saying sine of 16 degrees equals the opposite side, which is GF. So we'll go ahead and change that to GF. And the hypotenuse of that triangle is 20. So let's change the hypotenuse to 20. And then what I do to get GF on its own is I multiply both sides by 20. So it kind of sneaks its way in front over there. And that smells like a calculator problem to me, boss. Okay, chuck that in, press equals, and we get 5,51 units for GF. Okay, so now we're almost at the finish line. So you see the line BF, it's a radii, my bro, and the radius of the circle is 20 units long. And if this whole line is 20, just to get the green one, I can say the purple one minus the orange one. 20 minus 5.51 will give me the length of BG. Even though it doesn't look like it, they don't draw it to scale to purposefully confuse you in that way. So let's go ahead and get BG now. And at the end of the day, we get BG to be 14,49 units. And then our 4 marks come from the trig ratio used over here. The correct length of GF gotten over there. And 2 marks for the correct answer, 14.49. Coming in hot with question 10. COD is a diameter, that's important. EA is a tangent, that's also important information. And the rest of the information has been represented adequately on our sketch. So we're going to jump into the first question. Prove that TODF is a cyclic quadrilateral. If we scope out the cyclic quadrilateral represented in blue, I'm noticing that we have an exterior angle of it, which is 90 degrees. So if I can prove that the opposite interior angle is 90 degrees, then I've done it through converse exterior angles of cyclic quad, which is a theorem that states if your exterior angle equals the opposite interior angle, then you can jump to the conclusion that you have a cyclic quad around those 4 points. So over here, the mission is to prove that this is 90 and then our job is almost done. And we're going to do that with this little sneaky weasel, the diameter. If I follow the diameter down, yes, it's going to give me that crispy little 90 I'm looking for, but... And I knew that because of the theorem, angles in semicircle. If you have a diameter, it always subtends a 90 degree angle. So now I know that F2 plus F3 is 90 degrees for this reason. After I clap that statement and reason down, I'm going to show them the link between this 90 and this 90. So I've got to show them I recognize this was 90. So I'm going to say O1 equals 90 degrees given. And after I show that, I'm going to link these two. I'm going to show that F2 plus F3 equals O1 because they both equal 90. And now I'm going to leap into my conclusion. So I'm going to copy paste this. TODF is a cyclic quadrilateral. And then my reason for that line is the one we discussed earlier, converse exterior angle of cyclic quad. Having a look where the 4 marks come from, you get 2 marks over here for your way little reasons, and then we get 2 marks for this statement as well as this statement. Next up, we need to prove that angle D3 equals angle T1. Right now, D3, I'm noticing it's an exterior angle of that cyclic quad we just proved. And I know a theorem with the exterior angle of a cyclic quad. If I follow it to the opposite interior angle, they're going to be equal. So T3 will also equal D3. Using this theorem, exterior angles of a cyclic quad, the exterior angle equals the opposite interior angle. So let's make that connection, my butt. Okay, now we're almost done. Now we can see that T1 and T3 are vertically opposite one another, which means that those two are also equal to one another. We use like kind of letter X to see vertically opposite angles. So I'm just going to say T1 equals T3 vert op angles. And then since we know that T3 equals T3 and T1 equals T3, then it stands to reason that these two must be equal. So I'm just going to clap a therefore T1 equals D3, my bro. And yeah, we are done. Okay, 1 mark for your statement there, 1 mark for your reason over there, 1 mark for the statement and reason for that line. Now we need to prove that triangle TFO is similar to triangle DFE. So we're going to try to prove that 2 angles inside of those triangles are the same, and the third one will be equal by default because of interior angles of triangle. So let's get those highlighted to see what we're doing a bit better. Okay, and after highlighting those triangles, geez, check at this. D3 is already equal to T3. So we have proven that above. So let's state that quickly. There's one of our angles out the way. And as my reason there, I'm just going to put proven. In case you're curious, we proved it here with exterior angles of this blue cyclic quad that D3 has to be equal to T3. Alright, and I'm seeing a sneaky tangent. So with this angle inside of the purple triangle, I can apply the tan chord theorem. So the angle between the tangent and the chord will be equal to the angle that the chord subtends. So the angle between the tangent and the chord, so angle F4, identify my chord as DF, follow that on both sides up to the circumference, and it's going to take me to C2. So I know that F4 is the same size as C2. And we write it out just like this. Okay, and now there are some sneaky weasels, my bro. There's a couple of radii. OC is a radius and OF is a radius. So they have equal lengths, which means that the base angles must be the same. C2 will be the same size as F2 due to angles op equal size. And we're going to show it just like this. C2 equals F2, angles op equal sides. And now we're cooking, big butt. Now we've successfully proven that 2 of the 3 angles are the same inside of our orange triangle as well as our purple triangle. So I just need to show the link over here between F2 and F4. Since they both equal to C2, it stands to reason that these two have to be the same. And if 2 angles are the same, the third one is equal by default as discussed earlier. So this angle E over here will be the same as O2. And we simply just state that with the reason of interior angles of triangle. Now I can copy paste this statement. And I know that those triangles are similar because of angle. I proved all 3 angles are the same inside of those 2 triangles. So let's have a look where the 16,000 marks come from here. First mark comes from this statement. The second mark comes from the correct statement and reason over here. The third mark comes from this statement. Fourth mark comes from this statement. And then the 5th mark comes from this statement or reason. And this reason over here, you can additionally use a different reason. You can say third angle of triangle. It will also get you the mark over there. And now we've finished this chocho of a question. The next question tells us that B2 is equal to E. So B2 is equal to E, so it's also a red angle. And with that, we need to prove that the line DB is parallel to the line EA. So we're going to be using this very special triangle over here. There's some sneaky weasels in the mix. OB and OD are both radii, so their base angles will be equal. So D1 will be the same size as B2. Okay, and we simply just state that like D1 equals B2, and then our reason, we slap on that angles op equals sides. We've seen it about 16,000 times in this paper by now. Okay, and now after we've done that, the corresponding angles are equal. So I can see a F. Let me show you it a bit better. So it's a weird upside down F over here, and its corresponding angles are equal. And if the corresponding angles are equal, then we can jump to the conclusion that the lines are parallel. But before I jump into that, I just need to show the link between the corresponding angles. So previously they told us that B2 is equal to E. So I've actually got to state that with the reason of given. And since D1 equals B2 and B2 also equals E, it stands to reason that D1 must be the same as E. And now we can leap into the conclusion that DB is parallel to EA. And my reason for knowing that is because I proved the corresponding angles are equal. And let's have a look where the 2 marks come from. First mark comes from the statement and reason up top here, and the last mark just comes from that whale or reason. And bear in mind, if you don't have that equal sign, you're not going to get the marks, my China bean. Alright, buckle up, this is going to be a nasty one. Okay, so we need to prove that DO equals this mess. So what I'm going to do is I'm going to go back up to those triangles I proved that are similar, and I'm going to grab this and do the smiley face method. So after I grab those, I want to assess what I have over here on what ratios to choose. So I see I have a FE there, so I want to get FE in the mix. So I'm going to do the right eyebrow over the right eyebrow, so it will be FO over FE. And I also have a TO over here, and I see a TO with the smile here, so I'm going to put TO over DE. And then we're just going to get rid of these smiley faces over here. And that's how we write up the statement and reason. I knew these ratios existed because this triangle was similar to this triangle. And now I have 2 things that I want. I've got TO and I've got FE. Okay, but I don't want OF in the mix here. So let's go have a look at OF. Sneaky weasel alert, but okay, OF is a radius, OD is a radius, so I can change OF to OD. Okay, once that change has been made, then I've got 3 things that I want. I've got a DO, I've got a TO, and I've got an FE, but this DE is a bit of a problem. So what we're going to have to do is the proportional intercept theorem, line parallel to one side of triangle. And I'm going to do the proportional intercept theorem with these scallops over here. So let's get that written up quickly. OB over BA equals, it's going to equal this over this, because I did the big one over the small one. So now I've also got to do the big one over the small one. So it's going to be OD over DE. Okay, and now we're starting to cook a little bit. Now I'm going to kind of analyze this thing as well and see what I want and what do I want to get rid of. So I've got an OB here. I don't see an OB here, but OB is a radius. So let's go ahead and change it to OD because I want OD in the mix. Alright, I want AB to stay behind because I see a AB over there. Okay, this OD can stay because I want an OD, but I'm going to switch order so it looks like this. So I'll change this to a DO. And I see another DE. That's actually going to be the link between these 2 ratios. So he'll stay behind. And now we don't need the sketch anymore, so I've gotten rid of it. So what I'm going to do here is get DE on its own. And I'm going to do the same thing here. And then I'm going to make them equal each other to get rid of the DE. So let's start over here. We're going to cross multiply going up and we get the following. Okay, so DE times OD just gives you OD times the DE, likewise over there. And now I want this DE on its own, so I'm going to divide both sides by OD, or better yet, DO. And then these DOs over here, we're going to slap them out of there. And these DOs over here, they can also cancel. And now we have successfully found out that DE is the same size of AB. Then this oak, I'm going to slap him straight in there. Change this to an AB because I definitely want AB in the mix here. So after we just pop that in there, we are almost at the finish line. So now I want DO on its own. So I'm going to cross multiply that FE up to the top there. And finally, we've got our final answer. And my goodness gracious, this question was some other parked down prawn. Okay, let's have a look where the 16,000 marks come from. So you're going to get 1 mark for this reason here, line parallel to one side of triangle. Simplifying that whole ratio will get you another mark. Then you get 1 mark for the statement and reason for the similar triangles. Changing the radius over there will get you a mark, and then sort of simplifying that will get you another mark. You don't get a mark for the final answer because it was given to you.